Hello chemists, this is Ms. Placino and you are watching lesson 4.1, an introduction to bonding. In today's lesson we're going to talk about why and how atoms form bonds. We're really just going to scratch the surface and try to introduce some basics today, and we'll be building on that throughout the unit. Alright, goals for today's lesson. You should be able to explain why atoms bond with each other. You should be able to explain why breaking bonds requires energy and why forming bonds releases energy. And conceptually, this is often kind of a tough one for new chemistry students. We'll differentiate between ionic and covalent bonds. You might be familiar with those terms already. If you are, great. If not, don't panic. We'll introduce them today, and then we'll really dive into them more deeply in lesson 4.2 and 4.3. And last but not least, draw Lewis dot diagrams for atoms and monatomic ions. This is another big takeaway from today's lesson. We're going to be using these Lewis dot diagrams as kind of like the foundation for everything else we do this unit. All right, let's get started. Chemical bonding is really just attractive forces between atoms. We know that an atom consists of a positive nucleus and negative electrons. When you get two atoms close enough to one another, the nucleus of one atom can attract the valence electrons of the other atom, and vice versa. That second atom's nucleus will attract the valence electrons of the first atom. It's going to cause those two electron clouds, or sublevels, or orbitals, however you'd like to look at it, to overlap and share that pair of electrons. And when those clouds overlap, that electron pair gets shared, it's going to hold those two atoms together. And that's what a chemical bond is. More specifically, that's like what a covalent chemical bond is. We're going to be focusing on the main group elements again, just like we did in the last unit. To remind you, when we say main group elements, we're talking about elements with valence electrons in the s and p sublevels. It's really going to narrow down the periodic table for us. So we're going to look at elements in groups 1 and 2, our alkaline metals, alkaline earth metals. We'll skip over the transition metals, and we'll look at groups 13 through 18 as well. No D block or F block elements. Metals kind of, when they bond with each other, as most of the transition metals and rare earths will, kind of play by a different set of rules with metallic bonding, and we don't focus too much on that in first year chemistry. The S and the P blocks, however, when they go to bond with one another, they're usually driven by trying to fill that octet. In other words, get 8 electrons in the valence shell. We're going to kind of just, again, downgrade to the Bohr model of the atom, as it does a pretty good job explaining everything that we see in bonding at this level. Hopefully you remember from the last unit that when an atom fills its octet, gets 8 electrons in that valence shell, that's going to stabilize the atom and as a result lower its overall energy. And atoms want that. The lower the energy, the more stable the atom is, the happier an atom is. Of course, atoms don't actually have feelings, but I'm sure you get what I'm saying. We've seen these 3 Bohr models before. We've got sodium, a metal, and our metal, especially our group 1 and 2 metals, we're going to have 1 or 2 valence electrons. To get to that octet, it's easiest to lose that extra electron or 2. For our nonmetals, like fluorine, nonmetals tend to only be missing 1 or 2 valence electrons from its complete octet, so they tend to try to gain electrons if possible, or share if they need to. We know that neon is a group 18 element, also known as a noble gas. And we know that those elements are extremely unreactive. We say that they're inert. That's because they already have that complete octet in their valence shell, and they don't really have anything to gain by reacting with another atom. So again, in order to get to this stable octet of electrons, metals will tend to lose electrons. Nonmetals will try to gain electrons, so that's kind of the transferring of electrons, or if nonmetals are going to bond with one another, they tend to achieve this by sharing electrons. And we'll get into a lot more detail about different types of bonds as this unit progresses. Okay, you've got this chart in your workbook. We've got a hydrogen atom and a chlorine atom far apart. as we bring them closer and closer together, we can see that the energy, potential energy, is dropping. And when it gets to this like bottom, this trough, that's where the HCl bond forms. Anytime you go to form a bond, you are going to release energy. It doesn't matter what's coming together, metal with nonmetal, two nonmetals, so on and so forth. We always see a release of energy. If you think about what's going on, there's hydrogen, and chlorine has 7 valence electrons. I'm not going to draw all 17 of chlorine's electrons, but I will draw its 7 valence. What's going to happen to both of these elements' valence shell when that bond forms? Hopefully you're thinking that we're going to start to fill their valence shell. In the case of hydrogen, we complete what's called a duet. It doesn't have an octet of electrons, only 2 will fit in that first energy level. But in the case of chlorine, we're going to get an octet of electrons. And I'm just going to switch colors and put my shared electrons. Let's put them in like blue. Electrons that are being shared between H and Cl. So we know that completing an octet is going to decrease the energy of the atom and stabilize it. So it makes sense that forming a bond should release energy. I'm taking chlorine and hydrogen and I'm completing their valence shell. That's associated with energy, loss, and stability. If I try to go in the opposite direction, if I try to take my HCl, which is bonded together now, and I try to rip it apart, I'm going to have to put energy in, as neither hydrogen nor chlorine really wants to kind of exist as independent atoms. They would rather bond so they can lower their energy. So breaking bonds always requires energy to be put in. And these are two concepts that new chemists often struggle with. The formation of bonds completes octets, therefore stabilizing the atoms involved in the bond and releases energy. Breaking apart that molecule, that bond that has formed, requires energy as we're taking apart stable octets. Just a quick little piece of information about different types of bonds. Covalent bonds, we're talking about sharing. So electrons are going to be shared between atoms. So like we saw with that hydrogen and chlorine bond, we have a pair of electrons being shared. You've got that overlap of orbitals, those electron clouds, and that pair of electrons is our bond. Ionic bonds, those are formed when electrons are transferred from one atom to another. So sometimes we end up with an atom that has like an extra electron or just 1 or 2 valence electrons in its outermost shell, and it will tend to just give it away or transfer it to an atom that has a near complete valence shell. So just be aware that those are the 2 different types of bonds, and again, we'll spend a lot more time in lessons 4.2 and 4.3 talking about them. Okay, the last thing that I want to do today is to draw Lewis dot diagrams. You're probably tired of drawing Bohr models of the atom, going through and like all the rings and the dots and making sure the nucleus is there. It can be a lot to keep track of. We really only care about the valence electrons in bonding. The ones in the inner shells are pretty boring and tend not to get involved. So in our Lewis dot diagrams, we're only going to show valence electrons. What we're going to do is kind of imagine that there's like a little box around an element symbol. So I've got like top, bottom, left, and right. And we're going to put the element's valence electrons around this box on one side at a time and only pair them up when necessary. So if we look at lithium on the periodic table, and what I've got here is just going across period 2, lithium has the electron configuration 2-1 according to the Bohr model, so it's got 1 valence electron. I'm going to represent that by drawing a dot. There's lithium's 1 valence electron. I chose to put it on the left side. You might have put it on the top or the bottom or the right side. That's completely okay. Any side is fine as long as it's just got its 1 valence electron. We move over to beryllium, Be, 2-2. Okay, we're going to, again, kind of visualize that like box around it. 2 valence electrons. That's it. If you think you've got it, pause the video, draw out the dots for boron through neon. All right, boron, 3 valence electrons. One, I'll put one there, put one there. One on 3 of the sides. Just don't pair them up until you absolutely have to. Carbon, 1, 2, 3, 4. Okay, now I've got 1 electron on each side. I'm gonna have to start pairing them up. Nitrogen has 5 valence electrons. Does it matter where you pair? No, I'm gonna put the pair on the right side for no particular reason whatsoever. Nitrogen, you have to have one side with a pair of electrons, the 3 other sides, just 1 electron. Oxygen, I'll go top and left. As long as you've got 2 electron pairs and 2 single electron, you're good. There's fluorine with its 7 valence electrons. And finally, neon. You'll fill them up on every side. Take a look at the practice problems and try to do like that top row with the valence electrons. Lewis dot diagram. I will meet you there in a moment. All right, so let's take a look at just this top row. Magnesium, 2 valence electrons. Bromine, 7 valence electrons. Cesium, just 1. Sulfur, 6 valence electrons. Silicon has 4 valence electrons. I'm going to skip over sodium plus and O2 minus, the oxide ion, argon. Come back to those in a second. If you compare the Lewis dot diagrams that you just drew to the ones that you had from before, hopefully you have noticed a pattern. Elements that are in the same group are going to have the same number of valence electrons. So for example, bromine and fluorine are in the same group, and both of them have 7 valence electrons. Neon and argon both have 8 valence electrons. They're both in the same group. All right, sodium plus and oxide with a charge of 2 minus. We know the sodium atom is 2-8-1. When sodium becomes an ion with a charge of +1, we've got to lose that electron. The convention is to treat this last valence shell, the last one you write, as the valence shell, even if it's empty. So Na plus looks like this with no dots around it. Oxygen has a electron configuration of 2-6. It's the oxide ion with a charge of -2, so that must become 2-8. Its valence shell now has 8 electrons in it, so we fill it up. All right. And it'll work out that all of your cations are going to have an empty valence shell, and all of your anions will complete their octet so they look like the nearest noble gas. You've got that bottom row to practice with. Hopefully things are making sense, and we're really going to build on this on lesson actually 4.2 and 4.3, so really important skill. All right, chemists, thanks for tuning in, and I hope you found this helpful.